بسم الله الرحمن الرحيم. أصحاب المعالي والسعادة، الحضور الكريم، السلام عليكم ورحمة الله وبركاته. طبعا يتشرف مركز تميز الإضاءة في مدينة الملك عبد العزيز للعلوم والتقنية ومركز الدراسات والبحوث بوزارة الاتصالات بشكركم ولتلبيتكم وحضوركم في هذه الجلسة الحوارية اللي إن شاء الله اليوم تكون ملهمة للجميع. طبعا جلسة اليوم ما تتحدث عن التخصصات الأكاديمية أو الدرجات العلمية فقط، تتحدث أيضا عن شغف الإنسان. في نوعين من الأشخاص، في شخص طبيعي وفي شخص مميز. طبعا كلهم نفس الصفات، كل واحد عندهم 5 أصابع، عنده نفس الصفات، لكن اللي يميز الشخص المتميز هو الشغف. عرف يكتشف هذا الشغف اللي عنده وعرف يطوره واستغل استغلال في محله. طبعا ما ننسى أنه المحيط له دور كبير. احنا عندنا ومحظوظين بهذا الشيء، عندنا رؤية 2030 هي المحيط، وهي البيئة الحاضنة والداعمة لكل مبتكر ولكل شخص يسعى أنه يكون يصل إلى درجات عالية أو يصبح شخص متميز. عشان كذا إذا أنت حاب تكون متميز دائما كن فضوليا، تساءل دوما، واستلهم من القصص، خصوصا قصص النجاح. فدائما تساءل ما هي سيرتهم، كيف بدأوا، إلى أين وصلوا. اليوم نبدأ في جلسة حوارية راح يقودها الدكتور منير الدسوقي، ويستضيف فيها العالم البروفيسور شوجي ناكامورا، تحت عنوان من الابتكار إلى النوبل، مسيرة العالم شوجي ناكامورا. يتفضل الدكتور منير وبروفيسور شوجي ناكامورا. إذا سمحتوا لي أنا عندي بريف بسيط عن الدكتور منير وأيضا البروفيسور شوجي. سعادة الدكتور منير بن محمود الدسوقي وكيل الوزارة للتخطيط والتطوير، الدكتور أيضا أستاذ زائر في جامعة ماك ماستر في كندا، ومن أعماله السابقة تأسيس التعاون المشترك في الإضاءة المرشدة للطاقة بين مدينة الملك عبد العزيز للعلوم والتقنية وجامعة الملك عبد الله للعلوم والتقنية وجامعة كاليفورنيا سانتا باربرا. وحصل الدكتور منير الدسوقي على العديد من الجوائز والمنح العلمية العالمية نظير اختراعاته، منها جائزة خادم الحرمين الشريفين للمخترعين والموهوبين، وشارك في أكثر من 85 ورقة ومقالة علمية محكمة في مجلات عالمية، ولديه 25 براءة اختراع في المكتب الأمريكي والسعودي. ما شاء الله سيرة جدا مشرفة دكتور. أما البروفيسور شوجي ناكامورا فهو عالم ياباني أمريكي حاصل على شهادة الدكتوراه في الهندسة الكهربائية من جامعة توكوشيما في اليابان. يعمل حاليا أستاذ في قسم المواد بكلية الهندسة في جامعة كاليفورنيا سانتا باربرا، وهو مدير مشارك لمركز تميز الإضاءة في مدينة الملك عبد العزيز للعلوم والتقنية، ولديه أكثر من 500 براءة اختراع مسجلة في أمريكا واليابان، كما نشر له أكثر من 550 ورقة بحثية في مجاله. ويعد ناكامورا مخترع الصمام الثنائي الباعث للضوء الأزرق وهو البلو ليد، والذي أحدث قفزة كبيرة في تقنيات الإضاءة وقاده لنيل جائزة نوبل في الفيزياء في عام 2014، بالإضافة لجائزة الألفية للتقنية عام 2006، إضافة إلى العديد من الجوائز العالمية الأخرى. ويذكر أن هذه التقنية تعتبر من مصادر الإضاءة البيضاء الموفرة للطاقة. دكتور منير سيقود هذه الجلسة الحوارية. بالتوفيق دكتور.
Thank you, Tarek. I'd like to start by thanking our partners from CACST and our visitors from KAUST and UCSB for being here today, specifically you, Suji, for the honor of joining us in this workshop. Tarek mentioned that I have 25 patents and you have 500 patents. So thank you for that, Tarek. Maybe we can go back to the beginning. So 500 patents. What inspired you to be an inventor? Where did you start? Where did you start your education? Walk us through how you started.
Okay, so I studied at the University of Tokushima. University of Tokushima is a small local university, and my major was electrical engineering, and yeah, so that is my background, and yeah. So after graduation, I joined a small chemical company. The name is Nichiya Chemical Industries. And at Nichiya Chemical Industry, I worked for the R&D. R&D, at the time, they are making materials for conventional infrared and red LEDs. So initially, I involved to develop the materials, and gradually I was involved in that to make the real LED devices.
So maybe share a little bit of what inspired you to be a researcher and an engineer.
I guess research is like solving quiz. You know, from the childhood, I love to solve all kind of difficult quiz. You know, research is a real quiz. You know, I do the research and I got some kind of result, and always I'm curious why I got this result. So from childhood, you know, always when I watch all kind of nature. You know, for example, I was a childhood. I was born near the ocean. Every day I was watching the ocean, and the ship is coming and the ship is disappear. Why ship coming and disappear? You know, I'm very curious. So same thing. The research is same. The experiment, and any kind of result I got. And why I got this, I'm thinking about using my idea. So that is inspired to work for the research.
So you look for challenge in what you do. Maybe I remember in the early 90s when you discovered the blue LED.
Mm-hmm.
That was about 115 years after Thomas Edison first discovered the incandescent light bulb.
Yes.
So research back then was saying that this is almost impossible to do.
Mm-hmm.
And it took you over a decade to reach that invention. Can you share that story with us?
Yeah, because at the company, I was involved in this. So initial first 10 years, I had to develop a conventional infrared and red LEDs from the material to the devices. And so at the time, I read all kinds of scientific papers, and all scientific papers is biggest problem of LED is no efficient blue and no efficient green LEDs. If efficient blue and green LED are available, they have the huge market for LED. So that's the reason gradually I want to invent a blue LED myself at a small company. But I asked the boss, why don't you start a blue LED research at my company? And my boss said, oh, Nakamura-san, you are crazy. You know my company, no budget, no research funding, and no brain, So, but 10 years later, because first 10 years I developed three products, but sales are very poor, and all my companies, boss, manager people complain a lot. You have to quit the company. So before quitting the company, I wanted what I wanted. That is blue LED research, because and then, 10 years later, I asked the company's founder, why don't you, can I do blue LED research? He said, okay, and please give me $5 million. He said, okay. And I never been to foreign countries at the age of 35 years old, so I went to University of Florida for 1 year. And then 1 year later I came back, I started blue LED research, and the coincidentally I could develop blue LED. That is my, so yeah, that is my, yeah.
So maybe share the impact of this invention with the audience. I see it used in everything in this room.
Yeah.
But maybe we could hear from you what was the advantage?
Yes, because using blue LED, we can make a very efficient white LEDs. The efficiency of white LED is 10 times efficient, more efficient than in comparison with conventional incandescent bulb lamp. So by replacing all conventional lighting, we can reduce the energy consumption dramatically, So I think worldwide, I think we can eliminate the, I think 60 nuclear power plants in a couple of years. So wow. Yeah, we can save a lot of energy. So that's a reason I think you know, I could receive the Nobel Prize.
So I realized that you didn't get a PhD early in your career, you got it later. So it wasn't something planned, it seems. Why did you want to get a PhD? Were you interested in publications?
Yes, because I went to University of Florida 1 year from 80 to 89. So I had to work together with PhD students over there. And all PhD students asked me, you know, Nakamura-san, do you have a PhD degree? I said no, because I had only master degree. And then next they asked me, have you published any scientific paper? I never published, so I said no. I had never published any scientific paper, zero, at the age of 35 years old. And then those American PhD students treat me like a technician. In the United States, scientists, I mean, they have to have a PhD degree, you know? So 1 year later, I came back to Japan. My dream became getting a PhD degree. And not the invention of Burette, because I never expected I could invent Burette, just I want to get a PhD degree because, you know, University of Florida, all PhD students ask me those questions. So in this case, you know, in Japan, I could get PhD by publishing more than 5 scientific papers. We didn't have to go to university to get PhD degree. Just publishing more than 5 scientific papers, we could get PhD degree. So just a reason. So I selected the gallium nitride because at that time, 2 materials available to develop blue LEDs, zinc cyanide or gallium nitride. All scientists select zinc cyanide. But gallium nitride, only a few scientists are working, so that's the reason I selected gallium nitride. And then coincidentally, luckily, I could invent the blue LEDs using gallium nitride.
So when you got the call that you won the Nobel Prize, how did that feel and what were you doing at the time?
Oh, at that time, you know, I think the United States, the time was, I think, 2 a.m. or 3 a.m. So already, you know, before, you know, so I was expected to get the phone call, they called to my cell phone. So I was already, you know, expected because 1 month before the Nobel Prize announcement, you know, at my university, several colleagues got a phone call, strange phone call. This phone call, you know, unknown person asked, you know, would you tell me Professor Nakamura's cell phone number? All my colleagues said, no, it's private information. We cannot tell them. But later, no, they reported to the department chair, and the department called me. Oh, this time Professor Nakamura usually receive a Nobel Prize. You have to wake up. So already I was expected. So just 2 or 3 a.m. I got a phone call. And,
but typically engineers don't get the Nobel Prize, right? Were you expecting to win based on your work?
No, because, yeah, you're right, because the Nobel Prize in physics is only for theory, you know, basic theory. And so I didn't expect, but Japanese mass media, you know, every year, no, just 1 day before Nobel Prize, all the Japanese mass media surrounded my house, you know, after invention, since 93, every year. So they expected I received a Nobel Prize, but for 20 years I didn't get it, so I think almost impossible, you know.
Since 93?
Yes.
So after you won, what changed? Did you feel anything different? Were you given any privileges from the university? Or?
Oh yeah, university, you know. One big advantage, no teaching anymore. No teaching. University of California, no, only Nobel laureate is, you know, no teaching anymore.
That's it.
Yeah.
Did you get a bigger office?
Yeah. Also, yeah. Parking space, parking lot, parking become free. Also, some salary increase. Yeah, that's it. That's really merit at the University of California.
Okay. Well, I realized that recently big companies, cell phone companies, are using your technology in displays. What's the latest in the display market or industry, and what's the difference between what you did and conventional OLED displays, for example?
Oh, okay. So up to now, LCD, no? LCD TV, for backlight, they use the white LED made by blue LEDs. But recently, you know, Samsung announced the micro LED display. Product name is called Kabe. It's so beautiful, you know, almost, you know, micro LED. They use a small, tiny chip, you know, blue-green LED. Each dot composed of 3 tiny chips, blue, green, red LED chip. It's a very small one. It's called micro LED display. The big difference is, you know, energy consumption is almost one chips in comparison is a OLED TV and the conventional LCD TV. So it's a, so that's a big advantage. Also, very color is also very good because the direct blue green, beautiful blue green LED LED use. So color of the TV is so beautiful. So last time they had a consumer electronics show, this January. I went there and Samsung booth, micro display. Oh, many people came to this micro display because color is so beautiful. Also size is 100-inch big one. So that's the reason. That is a micro display is the next generation display everybody expected. But there's several problems, especially LED LED is the biggest problem right now. Yeah.
Mm. Okay, and I read a lot about laser lighting.
Mm-hmm.
It's a new technology that's coming.
Mm-hmm.
We saw it in some of the cutting-edge German cars.
Mm-hmm.
What is laser lighting? Will we see it in households soon?
For general lighting, it takes a long time because the problem is laser lighting is, with blue laser diode. Out power of blue laser diode is almost 100 times higher than the blue LED. So you use a conventional phosphor, powder phosphor is burned due to the high power irradiation of the light. So we need special phosphor for laser lighting. So only available phosphor is a yellow phosphor right now. So yellow and blue, so yellow, blue, mixing of blue, yellow, and we can make white. But the only yellow means there are a lot of missing color. So right now, laser lighting is only for outside lighting, like automobile headlamp. But inside general lighting, we need a full color spectrum, full color. A lot of missing color. So right now, we cannot use laser lighting for general lighting. So I think it's still for general lighting, it takes maybe 5 or 10 years because we have to develop new phosphors for laser lighting.
And in Li-Fi technology?
Oh, Li-Fi technology is great because Li-Fi is especially for, laser lighting is because boom, they talk about more detail. Right now, so Wi-Fi, right now wireless communication Wi-Fi. Wi-Fi is, we have this radio frequency due to regulation. And 3G, 4G, 5G is the maximum frequency of radio frequency. After 5G, no technology to increase the data transfer. And I talked with AI. AI is getting popular, AI, and AI, IoT. So AI, have to handle huge data. In that case, AI people is not satisfied with 5G. They need more than 5G. And more than 5G right now, no technology. And laser Li-Fi is the only choice. Laser Li-Fi is frequency 6 order higher than radio frequency. So means the frequency 6 order, the bandwidth is almost infinite, not infinity, but huge there. So in comparison, 5G data transfer to 5 gigabit per second, 5 gigabit per second. Using this laser Li-Fi, 1 terabit per second, something, unbelievable data transfer rate. So that's a Boone, Professor Boone is working for. He talked about more detail there.
So yeah, we're waiting for an exciting talk from him. Suji, you've been coming to the kingdom for over 7 years now. I have a few snapshots of your visits.
Great, yes.
I think the first time we met you in the kingdom was at the KAUST NSF event in February 2017. Mm-hmm. Almost a year after that, we signed an agreement between KAUST and UCSB on solid-state lighting.
Yes.
Since then, you've been blessed. You won many well-deserved awards, most notably the Nobel Prize.
Wow.
And you became a celebrity and started posting in cool pictures like this. But you still remained coming to the kingdom.
Yes.
We saw you in many events, many workshops, many conferences.
Yes.
You also explored our, when you won the Nobel Prize, on the way to Stockholm to receive your award, we were very honored that you stopped by the kingdom.
Yes.
You gave a talk here.
Yes.
explored our nature, our culture, our food. Sometimes a little bit too much of our food.
Yeah, you're right. Yes.
You've practically, over time, have become one of us. And you worked with our students, our researchers.
Yes.
I wanted to ask you, from the 7-year experience you had in the kingdom, how was it working with Saudi researchers, scientists, and students? And what did you like most about working with Saudi Arabia?
Yeah, Saudi students, we accept a lot of Saudi students at our university. They are very hardworking and they're very smart. No doubt. Today, I think, Abdullah, and Mohammed, two Abdullah and one Mohammed. They are so great. Yeah. Maybe, sometimes but the average is so good. Yeah, Professor Jim Steve Dembas, I agree. They are so great. They recently created a lot of, got us great results for us. It's amazing. They are hardworking and smart at the same time. They at the lab, they work very hard. Also, they have a lot of great ideas to make a great new LED and bulk crystal growth. They're very good. No doubt. Yeah.
Thank you. It's an honor hearing that from you. Maybe the last question I'll ask is for the young engineers, young students, fresh graduates, early in career. What advice can you share with them?
I think already Saudi students demonstrate because they work very hard for lab experiment, and they got a lot of experiment, and they think about the experimental result, and they work for next research concerning about the experimental result. That is most important because the experimental result, think about the experimental result data, think about that one. That one is the most important for scientists. That is his thinking is a creative idea because her own idea. Think about the experimental data result using your own idea is a creative idea, and this is not. They reading papers, books, papers, reading books. Thinking about those things is not good. It's not creative idea because others' idea. Also, sometimes they are wrong. It's a wrong. A lot of data wrong papers there. But thinking about the real experimental data is not false. It's a real one. And using your own idea, it's a creative idea. Creative idea generates only creative thing, a breakthrough. So that's the most important for you.
So tangible results using own ideas and creativity.
Yes.
Okay, great. Thank you very much, Susie. So we have 10 minutes of Q&A with the audience. Okay.
It's really inspiring story, especially when you are staying in 7 years in Saudi. I think you've been likely with the traditions in Saudi also.
Thank you.
نبدأ فتح باب الأسئلة إذا تسمح الدكتور.
تفضل.
اللي عنده أي استفسار المايك موجود مع الشباب ممكن يعطونكم إياه. في أحد عنده استفسار لبروفيسور؟
السلام عليكم. شكرا. أحب أشكر الوزارة على إتاحة الفرصة هذه لنا. إحنا من خارج الوزارة. أنا الدكتور إبراهيم التركي. كنت أستاذ جامعي. Maybe I should speak in English ولا؟ طيب.
Japanese is good as well.
Yeah, maybe it's easier. Okay, my name is Dr. Ibrahim Al-Turki. I was a university professor. Now I have my own consulting company in consulting and science. And this is a very interesting subject, and we really appreciate the ministry's effort to promote these activities. My question is related to how could we make children and young people more innovative. For example, in Saudi Arabia, if you take the statistics, we are still we don't generate enough patents compared to other countries. Is there a way where we can make, especially the young, more creative in order to help in promoting our scientific endeavors?
Okay, I told you, so I think, so IP patent is like a quiz, you know. You know, so I told you, so very easy, you know, so patent is very easy, like a patent is, what's it? So for example, university, you know, every time when students write a paper, submit a paper, scientific paper, we ask to write a patent before submitting a paper. You know, some students, initially, you know, long-term students complain a lot because this is a scientific paper. How can I, no patent is okay, but how, they don't know how to write a patent. Yeah, patent, you know, just, it's like a quiz, you know, because anything you can write a patent, you know, it's probably hard to explain, you know. Not science, this is not science. Patent is like a quiz, you know. For example, you can patent like watching this one, you know, just not science, you know. Anything okay. So I think for young scientists, you know, if you want to generate an IP, it's not just do the experiment. You work for science experiment and get some data. You know, think about writing a patent. After writing, writing patent, no patent paper, no paper. Same time, think about how to write a patent. But how to write a patent is what's it? No. Somebody required like me. So some teacher is required, no? So who is the expert of the writing a patent is required. But for UCSB, you know, initially when I joined in UCSB, you know, number of patents was not so big, you know. So after joining UCSB, I asked each student write a patent, yeah. Every time when I write a paper, I asked write a patent, you know. Initially, they didn't like it, but maybe a couple of years later, you know, some company, you know, gave us a license, ask a license, and they paid the license fee, and you know, always a patent the inventor of the 10 or 5 students involved every time, and those students get some money. You know, and it's also, you know, it's small money, like $100 to $500, and those students tell the other student, and this spread it, and each, wow, and they became so happy, and then since that time, all the students want to write a patent because they get small money. So I think, you know, those, somebody had to do the similar thing at first, and they spread out, you know, and everyone want to write a patent. You know.
Thank you. في أسئلة أخرى؟
First of all, thank you for coming to MCIT. I would like to request you kindly to talk about some topics related to theoretical physics, like string theory, dark matter, dark energy,
Yes.
Antimatter. These topics, I just want to hear briefly any of these topics. So please.
Yeah, when I was childhood, I was dreamed to become, you know, those scientists to solve the mystery of the space, Earth, everything. That is my goal. And from childhood to the high school, always I dreamed to become those scientists to solve. I want to invent one equation to explain the whole space. That was my dream. But when I graduated high school, you know, my advisor, you know, high school advisor, you know, teacher said, no, your major should not be physics. You can't find a job. And he asked me, why don't you go to engineering university? Engineering. Your major should be engineering at university. So I was a high school here. I'm like a child, you know. So I followed his orders. So I changed my major was engineering, and I entered the University of Tokushima, my electrical engineering. But still, at that time, I was wanted the physics, basic physics. But and after graduation, I joined the small chemical. Always after university, I was still wanted the physics. Always I do physics because that's my dream, After joining a small chemical company, still I was reading physics books. But my boss always asked me, when do you make a product? When do you make a product? I was alone to make a product. I had to move around, equipment. I had to make something, So no time to physics. So after joining the company, my focus became making product, so means the engineering. So I forgot the physics.
So you think theoretical physics is useless?
No, depends on people's dream, My dream was physics, but I had to change my physics from the engineering. So, physics is, as a dream is very important to study physics, basic physics. Yeah.
Well, engineers just helped theoretical physicists take the picture of the first black hole a few days ago. So, so they all work together.
Yeah, but most important thing is the experiment, Experimental results is most reliable. Theory is about, About. No 100% of theory. Always about. 90% right. But experimental data is 100% true. That is my thinking always.
Arigato.
Yeah.
Any other question? Any questions؟ طيب أتوقع دكتور منير نشكر الآن.
Can you join me in thanking Suji? Thank you very much.
Thank you. Thank you. Thank you.
طيب حضورنا تسمحون الآن عندنا محاضرة للدكتور بون أوي. طبعا الدكتور بون أوي حاصل على شهادة الدكتوراه في الهندسة الكهربائية من جامعة غلاسكو في اسكتلند. يعمل الآن كبروفيسور للهندسة الكهربائية في جامعة الملك عبد الله للعلوم والتقنية، ويدير معملا لأبحاث الضوئيات فيها. أيضا يقوم المعمل تحت إشرافه بإجراء الأبحاث حول تقنيات الاتصالات الضوئية والبنيات النانونية الدقيقة للشرائح الإلكترونية. أسهم البروفيسور أوي كثيرا في تطوير التقنيات العملية للشرائح الإلكترونية المتخصصة في الاتصالات الضوئية، ونشر أكثر من 220 ورقة بحثية في مجالات ومؤتمرات علمية، وهو زميل في عدد من المعاهد والمؤسسات العلمية المتخصصة في علم الضوئيات والفوتونات، من أهمها الجمعية الأمريكية للضوئيات اللي هي Optical Society of America، والجمعية الدولية للضوئيات وعلم الفوتونات، كما يعمل محررا لعدد من المجلات العلمية المتخصصة. رحبوا معي بالدكتور بون أوي. You may come to the stage.
Okay, that's mine. Hello, can you hear me? All right. Thanks very much for the introductions, and I'd like to thank Dr. Munir for inviting me here to speak in this ministry, and it's truly an honor to be here to talk to you. Today, my talk, I'm going to focus very much on the beyond 5G, and I have to mention that this work essentially is the collaborative work between UCSB, CAUS, and CACS. And most of the funding is actually from CACS. Dr. Ahmad Al-Mani is here, and Munir was the former director that's funding this particular effort. So I believe this audience know what is 5G, and in my presentations, the objective that I set to myself is to briefly introducing what is 5G and then what are beyond. And also, well, since 5G is quite broad, we will not be able to do everything. So the objective will then be identified what are the opportunities that we could have, and we'll be able to leverage on our current efforts and so that the kingdom will be able to contribute on. So 5G, we know that for 4G, we connect people. So 5G, we are very much talking about broader than that, not only people, but the entire society. So bandwidth will become the major things, the major challenge that we will need to resolve. As Suji mentions, if you look at this very reliable data from Cisco that keep tracking about how many devices, particularly on the mobile devices out there, the orange color is the 4G. 4G is still increasing steadily, and by, say, 2-3 years later, you'll hit the same population as the world. There's 7-something billion. And the blue color light, a line indicating the deployment of 5G. 5G begin to introduce slowly, beginning this year, 2019. And we know that there are 5 major players now that provide equipment and facility. 2 are in China, Huawei, ZTE, and another 2 also in Asia, Samsung, or Nokia is not Nokia, and Ericsson. So begin to be able to see a significant increase in 3 years later, 2021. So what are the opportunities and challenges that we need to address in order to tap onto this particular opportunity? The other drive is essentially the data traffic. Data traffic we see steadily grow as well. That primarily from the smartphone, or the so-called phablet, phone and tablet joined together to form this phablet, is increasing almost exponentially. So all of those drive the need for larger bandwidth and capacity for the network. What are the drivers? Smart city is one. There are many different things. Suji mentions about the artificial intelligence and other bandwidth-hungry applications for 5G. But essentially, you now can integrate everything into the smart city. Smart city, we are very much talking about people. We are talking about the society, talking about security, talking about various different things that will be able to integrate all those informations to get, integrate the informations that require the very reliable, large bandwidth connections to make things happen. Let's segment into one of the very, very hot topic this day is autonomous vehicle. According to Intel, a single vehicle, if you want to make it really safe and truly autonomous, the bandwidth or the bit rate, data rate that required to make this happen is at least 100 megabits per second. So that, again, is the single vehicle by itself. If we're talking about the entire traffic system, vehicle will then be able to communicate with vehicle so that be able to make things safer, and also being able to communicate through the other infrastructures, for example, the traffic light, etc. So that will add on to other demand of bandwidth. But of course, until today, we're still very much relying on the RF spectrum, which span from maybe 3 gigahertz, go all the way to about 300 gigahertz or so to make all those communications. But free space, optical communications might be another technology that be able to complement some of the bandwidth within the entire wireless system. In a nutshell, let's review. Because until today, although ITU and etc., they try to come up with a standard for 5G, there is no clear standard quite yet. Still keep on. Various different country, people, and organizations try to contribute towards the to standardize what is 5G, but it will be quite difficult. During the transitions from 3G to 4G, for example, they always go into, say, how many times of the bandwidth is needed, and what is the capacity, and etc., etc. 5G, for transitions from 4G to 5G, people are very much looking into the same thing. So let's look at the data that given by Ericsson. Ericsson is one of the vendors, after all. So what is their view on 5G? 5G essentially is, excuse me, I need to remove this box. They still very much go for the same approach. Take, for example, the data. Data, they wanted to see at least a 10x to 100x increase in bit rate. So that will then, in total, they call it as the 5G standard. And low latency, 5 times lower. And talking about the data capacity, or the so-called mobile data volume, they're very much talking about 1000x. Actually, other vendors even specified up to 10,000x or so. So it's between 1000x and 10,000x connected devices, 10x, go all the way to 100x. And one of the very interesting things is the battery lifetime has to be extremely low power, because they are very much talking about 10 times lower power. The device has 10 times lower power than the existing 4G devices. So all those will actually provide different opportunity and challenges to the next phase of the transitions from 4 to 5G. Let's talk about the capacity to start with, the data and also the number of devices that's been connected onto the network. We're very much talking about a city that is connected by a lot of points and massive MIMO. MIMO stands for, as you know, multiple input, multiple outputs. And in order to increase the bit rate or the data rate, you go into the small cell concept. Small cell means that instead of having the single tower that cover a couple of miles of radius, you now have many of those small cells that broadcasting, so that to be able to have very high bit rate transmitted to the user. And also, if you reduce the distance from all the small cell to another, the latency, meaning the delay in transmitting signal from one point to another, will become lower also. So small cell concept will become quite hard. But one problem happened though. By using the current technology, you're talking very much about the radio wave, millimeter wave, and microwave. So imagine all those tiny little cells that's a few 100 meters, you have one, and every single cell, according to the standards, you have to have a transmission power of up to 25 dBm. So what is the meaning of 25 dBm? You're very much talking about 300-something milliwatt of power. That's a huge lot of power that's transmitting everywhere. Imagine the entire city, the metro region, as a microwave oven. You essentially will expose a lot of people in this microwave oven. That is health conscious. And of course, the system has to be fully duplex, transmitting and receiving capability, and also because for such a big bandwidth, although we'll be able to provide such a big bandwidth, but they're still concerned about the security. Which one should tap onto the bandwidth first? For example, ambulance, communications through ambulance, that has to be the priority. So network slicing will then become important. That although it's defined by the software, but that again is a huge lot of opportunity that people can tap on. So since we are in the microwave oven, this is brand new, 15 days ago, 1st April in Belgium. In Belgium, they're very much worried about those radiations and stop the trial in Brussels. So the 5G trial is stopped just because of too much radiations that they're worried that will harm people's health. Of course, this is very much the 30 gigahertz all the way to 300 gigahertz radiations. So opportunity come here. If we be able to use light doesn't create any harmful radiations to our body. That will at least ease some of the requirement of using radio wave, millimeter wave, and microwave in transmitting some of the signal. Another thing is the latency. Latency essentially still go back to the speed of light in this case. And we know that the fastest speed is actually speed of light, 3 times 10 power 8 meter per second. And the requirement for latency, as for 4G today, 4G, the current latency is about 40 to 50 milliseconds, which is actually quite doable. And when you roll into 5G, we're very much talking about 1 millisecond or shorter, meaning you cannot afford to have such a long delay. Delay actually incurring a lot of roll into other problems as well. For example, certain thing stock, for example, if you want to use 5G signal to make certain decisions, investment, buying stocks, and etc., that millisecond of delay can result in a lot of loss. So 1 millisecond is definitely doable for light, because light is traveling the fastest speed. And for 1 kilometer, if you calculate the speed of light, we only have about 3.3 microsecond of delay. So 3.3 microsecond of delay to meet this latency of 1 millisecond, light have the advantage compared to other technique. Data rate. Data rate is everyone's concern. So data rate, if you look at again, that's from Cisco. They keep tracking of this number, which is quite real because they track until 2007 and project from 2017 onwards. 4G now gives us about a few tenths of megabit per second. Those are the peak data rates. And as for the 5G, we are very much talking about 10 times of the current data or 100 times of the current data. We very much are talking about at least 100 megabit per second of data. And also in the peak, data rate has to go up to 10 gigabit per second. So that's huge, lot of data that we need to, data rate that we need to increase from the current data to this number. Verizon, they announced that when they roll into from 3G to 4G, even 4G today, the published number is very large. From download, you have about 5 megabit per second to about 12 megabit per second. That is 4G. And for upload your data to the system is very much ranging from 2 megabit per second to 5 megabit per second, which is really low. So anything above 10x of what people are doing would then roll into the 5G system. But in 2017, 70 megabit per second will become the very minimum data that people are aiming for. In fact, today's, Japan have just announced a trial that managed to get about 460 something megabit per second. That is for their Docomo. That is for their 5G system. But anyway, at the steady state, 5G should hit at least about 100 megabit per second, which is a lot of increase from the current data rate of a few tenths of about tenths or so of megabit per second. So that again opens up a very huge opportunity if you want to reduce the radiations, yet still keep to this particular bit rate by minimizing the usage of the small cell concept, then maybe other alternate technology need to be there. The last one that I'd like to mention is the battery lifetime, 10x. 10x battery lifetime, how are we going to achieve it? They're very much talking about 10 years machine to machine or device to device lifetime. And you can look at it as joule per bit or bit per joule, depending on which angle are you looking for. Essentially, it has to be 10 times lower than the existing number processing a single bit. That also opens out a big opportunity for various different institutions, organizations, and research groups to look into how to make the device flat energy. Means that I do not need to consume any external energy. So I will be able to harvest energy by using certain mechanism and make it cell power. So that's a topic that the center, Carlos Cax and UC Santa Barbara has been looking at. Very quickly, those are the data demand for 5G. We know what is the core transport. Core transport basically from the long haul into the core. We are very much talking about 1 pentabit per second of bit rate. And metro, we should get into terabits per second. terabits per second or so, you cannot go with any other wireless technology but fiber. So those are all fiber. So it's optical access network downwards. They're all fiber. And go into the wireless access. As of today, it's still very much in the RF regime. So for example, in the residential area, business, and etc., mobile backhaul now using wireless. Wireless can be in the microwave, millimeter wave regime, and also if from our point of view, would it be possible to replace some of those wireless networks by using optical technique? So let me summarize a little bit about challenges or opportunity that we see. Tendency, light has advantage. Bandwidth, terabits has been demonstrated by using light technology, either free space or guided optical signal. Radiations, if we're using light, essentially we can get rid of or reduce a lot of radiations to the entire the wireless network system, wireless access network. Energy, there's opportunity for us to look at, because light actually delivers a lot of energy, be able to think about how to make the self-power or so. That would be opportunity that we'll be able to see. One thing remains challenge is the omnidirectional, because light, unlike the lower spectrum, lower end of the radiations, you'll be able to penetrate wall, etc., to go into the omnidirectional method. But in this case, it still very much have to be omnidirectional. I propose a couple of the possible solutions to address this directional issue. Let me quickly introduce these two things. For optical communications in free space, we call it as an optical wireless comm, or OWC. We have point-to-point connections. That is the free space optics, or FSO. We're still using near-infrared light. Just for your information, near-infrared light is, especially in the long wavelength 1.5 or so, those are so-called eye-safe radiation. It means that you're allowed to get into your eyes by quite a bit of power without damaging eye. So that FSO link essentially is from one point to another. It can send up to, say, kilometers or so. And those links will be able to get up to a few gigabit per second, a few tens of gigabit per second, terabit per second, depending on the modulation scheme that you are doing. Another one that we keep on hearing now is the so-called Li-Fi, or sometimes in some of the literature that refer to it as visible light communication, VLC. VLC essentially is still using visible light, LED, or laser, which is from the UV, in violet color, go all the way to the deep red signal. Again, we know about RF, up to 300 gigahertz, and that requires license. 5G, in order to enable the 5G networks, many countries begin to open out some of the spectrum that's still very much focusing on the radio wave to microwave, up to 300 gigahertz. So, and optical wireless comm from infrared go all the way to ultraviolet. It's mentioned it in terahertz, so you have enough bandwidth, a lot of bandwidth to support those data. Yeah, that's unlicensed. Basically, you then be able to use this without going through certain authority to approve those bands when you're using it. Data rates, gigabit per second for optical wireless is quite common. This is what we did in KAUST. We have the free space optical communications. This is the building. Anyone visited KAUST before, knowing that this is building 3, that is the locations of my labs. And then we shoot it to another building called building 2. Very short range, about 70 meters or so. And we established the FSO, the so-called free space optics link, for up to 3 months or so over a very, very harsh period of time, because it's a very unique environment here that allows us to study the channel, the environment, the turbulence, the humidity, temperature change, and etc. So we keep on collecting data. And again, this is in near infrared, 1550 send, and then receive by using 1310. and over the long period of time of monitoring. And we're still setting this to continue over the year of monitoring now. Bit rate-wise, because we are focusing very much to understand the channel, meaning the environment in Saudi, whether be able to do so easily. So the bit rate that we are sending is in only 1 gigabit per second. Wi-Fi achievement in the past 3-4 years, when we work together in these 3 universities, has been working on a lot of those things now. So it's a bit boring, so I will not go into detail, I will only present the result. If you compare some of the Wi-Fi company in the world, Pure Wi-Fi is the leader. Pure Wi-Fi is the leader because of Harold Haas. Professor Harold Haas is the guy who came up with this name called Wi-Fi in Edinburgh. And they're still very much the early company get into this market space. Many of them still very much in the using the LED. Cow spin off Sonor. Sonor, I believe, that's my student told me that SA stands for Saudi. Nor here is light, so it's Saudi Light Company. Sonor, in the lab, we demonstrate about 12 gigabit per second, but the company now have a link that will be able to provide up to 2 gigabit per second with a long distance of 20 meters. We are going to showcase this in tomorrow workshop in CACST. So if any one of you are interested to see the live demo, feel free to attend that the workshop. So this is what we are achieving. Most of the company all over the world, US, UK, and everywhere, is still very much talking about very, very short distance. In fact, in the building, if you're talking about Wi-Fi in the building, a few meters is substantial. But in our case, no. We, in Sonor, at least we have 20 meters throw. But in the lab, that's very much research paper. We have 100 meters or so, and still being able to keep above 1 gigabit per second link. Then the rest are still a few hundred megabit per second, and we are already in gigabit. Let me quickly go through some of the results. We work together on a lot of the component development, but this some of the results, the very new one a few months ago that we begin to roll off some of those results. We begin to look into how to send even faster signal by using the transmitter, which is the heart of the entire system called semiconductor laser. Unlike the near-infrared semiconductor laser, you'll be able to go up to, say, a few tenths of gigabit per second of direct modulations, but there's no such thing in broad area visible laser yet. As for this case, we create some of the grating to control a single wavelength so that be able to support a very, very sharp wavelength. We get 30 picometer or so of line width, so it means that the color is very, very pure after this one. And by doing so, we are still in the process of checking the bit rate, be able to bit many of the semiconductor laser with broad bandwidth or broad line width in terms of bit rates. Another reason for working on the green color is that there is a missing spectrum in the sun that is called Van Hove line that is missing, so that by sending this particular signal through the visible light, we essentially be able to send those signals and detect it without needing the filter or very complex optical system because it's missing from the sun, so there's no sun interference in the system. Another thing that we have been working on is one of the CAC students, Al-Tawi, is creating entirely new source. We have laser, we have LED. Something in between is so-called super luminescent diodes. So it balances both ends. Laser, when you hear about laser lighting, for example, when you hear about laser applications, people always have this concern, the health concerns, basically worrying that the damaged eye. But this class of device, we very much balance everything. Broadband, this is SLD, and slightly broader with higher power, that is a superluminescent diode that we call SLD, and then laser have very, very pure wavelength. That's all the energy focusing on the single wavelength. That is quite, that's laser. And we create this new class of the device to send very fast signal. And this, the bandwidth, the frequency response get up to gigahertz. And we also hold the bracket of very high power, up to about 470 milliwatt or so, which is quite comparable to most of the semiconductor lasers power in visible range. But in this case, it's not the laser source, but the SLD source, the broadband light source. In terms of color, the color rendering index, we hit up to 91 or so, but of course 100 is the maximum. But in this case, we hit about 91. Yet, being able to maintain a gigabit per second transmissions. Omnidirectional receiver. We are going into developing our own receiver because there is a missing component for visible light communications in high-speed photodetector. Most of the high-speed photodetector, as of today, has quite limited bandwidth and it's very expensive. So we work on the micro PD array, and I believe 3.2 gigabit per second of this receiver is still one among the records. We also begin to work in the UV regime. Why UV? UV, you have the omnidirectional, meaning you have the so-called non-line of sight. You do not need to have point-to-point link. You'll be able to, through scattering, you'll be able to receive those. But you need a very, very high-speed photodetector, which is, as of today is still missing. And we begin to look into it. We also have just currently demonstrated this very, very interesting idea. Since we do not have very high-speed photodetector in UVC, UVC is solar blind. So solar radiation is missing this particular band, which is 200 nanometers, go all the way to 280 nanometers of band wavelength. And in most of the silicon-based photodetector, the responsivity, meaning the sensitivity for this particular photodetector is less than .something%, which is too small or too low to convert those UV light. And by using the technique that we apply, some nanoparticle coated onto the devices, we'll be able to increase the responsivity by 4-fold. So which bring it back to the normal responsivity by using silicon photodetector for, of course, non-line of sight. And we're still being able to capture, go up to about 30 something megabit per second. By the way, to send a high resolution video, we only need about 10 megabit per second. This is a project that we have not reported, but it's somewhat interesting concept. We use solar cell to harvest energy and also to use it as a detector. And at the same time, we design our own signal processing unit that require only about 0.37 watt of power. And since we have the capability of sending white color light through our laser white light towards the photodetector, and that will provide enough energy for the photovoltaic or the solar cell, as well as to power the entire receiver up and be able to use it to provide quite a big heart rate, quite a high bit rate as well. Up to 20 meters or so, be able to get close to megabit per second. How significant is this? Imagine this. You'd be able to have the entire portable devices that coated with solar cell, and that itself giving you a broad area receiver to provide up to, say, 5/10 megabit per second or so of bit rate, and still being able to use as a power harvesting or energy harvesting device to power up your portable devices. That will be the goal that we hope to be able to do it. Couple of universities are competing in this space, but usually they are very much talking about very short distance, a few tenths of centimeter. We very much go beyond a meter. We actually go up to a few tenths of meters. Beyond 5G. What else can we do beyond 5G? We want to bring internet to underwater. Why underwater? Underwater, you might not be aware of it, but there are millions of others probe. That's communication node that is now implanted in underwater. How nice if be able to dive underwater and being able to surf internet at the same time, or making Skype call if you need help. So that is the objective of the entire things. And we bring internet to underwater and call it as internet of underwater thing. Well, a lot of waters cover the entire Earth, and there are a lot of applications. We can communicate with the moon. That's easier for us to do so than communicate through underwater. That's one of the motivations. We did that. This is the first Skype that we call in underwater medium. Very simple. In this case, we have the iPad and go through, of course, the entire casings using a very simple concept of Raspberry Pi, if anyone familiar with this electronic module to convert the signal, and using optical means to connect both the connections. And you then be able to download video, for example, in underwater, and also being able to make Skype call, for example. High-resolution video is not quite there yet because this is very much limited to the first trial that we have in underwater. Is still very much limited in bit rates. We are going to improve the electronics so that be able to hit at least a few tenths of megabit per second. So means that one day, diver need help, even in the water, be able to directly communicate with the surface by bringing the internet to the underwater. We're quite proud of this particular trial. This is from MIT Lincoln Lab. They're very much using the same technique that we developed. We are the first to report the high bit rate underwater communications. But if you want to show this, bring you to this particular stainless steel beam that I put underwater for a very short bridge, 5 meters or so, 4.8 to be more precise. They managed to get about a few tenths of megabit per second. But they begin to construct this particular chart. And work done at KAUST, for example, we now still holding the record of the bit rate and also the distance. Distance we reach about 20 meters. 20 meters, the benchmark is that we want to hit above gigabit per second. For your information, some of the acoustic method of communication underwater is only a few kilohertz or a few kilobits per second. That's not enough to support video. And as for our case, we have more than enough bandwidth to make high-resolution video. I will skip this one because, maybe briefly, in underwater medium, everything is moving. To align point to point is almost impossible. So we developed a technique to very much converting the incident light into different color and guided inside the entire waveguide so that be able to use a tiny little devices with aperture size that is not any bigger than, say, 0.5 mm or so to detect high-speed signal. That is essentially to address the problem of the so-called positioning, acquisitions, and tracking within the moving media. Non-line of sight. So hopefully, if happen to have diver, still being able to establish the communication link, even with the internet and etc., if we have the non-line of sight, so that signal is scattered towards the diver, etc. So we are also among the first to demonstrate the non-line of sight, of course, in this case by using a UV light. Very briefly, so another thing is, if we want to bring the sensor, a lot of sensor, which is already happening anyway in the world, to underwater, how are we going to communicate with the space? Our idea is that we hope that one day we have all those probes placing underwater and still the signal being able to cross the surface, the interface between the water and the air. And by flying a drone, for example, we'll be able to pick out all the signal, not necessarily have to go underwater. MIT Media Lab, about a few months ago, 4 or 5 months ago, they used a technique. Those technique that they're using is using an acoustic wave, vibrating the surface water, and then use the detector to pick up those vibrational, which is very nice idea, but actually it's a very big thing. CNN even interviewed them, etc. But how practical it is? They're demonstrating it in less than a meter, saying about 30 centimeters of water media, and then about 30 centimeters of the space media. As in our case, we go differently. By using light, lights can escape from the water surface while even making wave, yet being able to detect from the surface. This work we have just submitted for quick publication, so we don't quite care about where do we submit, but Opti Express is the place where we hope to be able to get it done. So that is the quick demonstrations. In terms of transmitting distance, if they're able to scale power, if they have able to get a higher power, UV LED, for example, which I really asked from a colleague in UC Santa Barbara, we should be able to stand longer distance. But in this case, a quick demo, we managed to get above 100 megabits per second. We also now building our own probe and in underwater. So that essentially is hope to be able to drive the internet technology go underwater and to make us understand a lot more and make the entire network more vibrant by having the entire system from the water to air to satellite. Actually, we're now developing Sago. Basically, it's a chip. It's the commercial, not commercial. It's the commercial satellites that will be able to tap onto, so that be able to have the entire 3 layers of things linked up together, from underwater to air to satellite, and then back to ground, and etc. And hopefully, be able to develop this and demonstrate this in the next 1 year or so. With this, I would like to conclude my talk by playing this video. There's no video file. Okay, that's PDF. So this is very much the video file that we have our link, internet link, that to summarize what I say. We have the link using white light laser that give us beyond 2 gigabit per second. And also we demonstrate some of the link for free space optic from our lab building, go all the way to the other building. And next step, we hope to be able to go for 1 kilometers of transmissions, go through the Cow's beacon. But funding's quite lack of, so lack of funding. So that will be the natural step. With this, I would like to thank very, very valuable collaborator of mine from CACS, Dr. Munir Ahmad, Dr. Ahmad, Kaus, Slim Aluni, Osman Bakr, and UC Santa Barbara, Steve, Suji Nakamura, Jim. Thank you. Yeah. Any question that I can answer? Yes, Steve.
Yeah, from satellite to the surface, have you done any experiments on? For satellite to ground, have you done any experiments on the blue laser through cloud or atmosphere transmission yet?
That's wonderful. In fact, we are now getting ready to communicate directly from the next step that we are doing is from underwater through drone, and drone communicate directly with the satellite. That we need time. So that is next step. In fact, those are all inspired by one of the, it's actually China. They have this three dam. So they have huge dam. They have a lot of tunnel. They usually will have to send a submarine inside the tunnel to study the integrity of the structures, but be able to implant some of those probes, flying a drone that remote control, collect all this data, include the real images. That is the first thing that we are looking into. And then communicate with satellite would be the next step that we are doing it. But communicating with satellite, we cannot go for optical. So if your question is whether we use optical, no. We're still going to go for RF. Okay. Mm-hmm. Yeah, thanks.
نشكر كافة الحضور. We would like to thank also Professor Shuji with Dr. Bon.
Thank you.
It is an honor to have you here today. We would like to take a group photo with you all in the stage.